Okay, so we're recording back, and we are starting a new lecture on optimization problem. And I want to start this discussion by defining what do we call transportation problem. So if you were to sort of search for transportation problem, you're not going to find the problem that we typically talk about. Hey, safety is a transportation problem, or congestion and or whatnot. Transportation problem is actually a mathematical problem which describes how do you ship the goods from maybe factory to the warehouse or something like that. Okay, what is the optimal way of shipping goods from point A to point B given certain constraints and given certain costs of shipping? Okay, that's what we call transportation problem. By the way, that's the problem that FedEx is trying to solve, or even Amazon is trying to solve, and all these other people are trying to solve. And then the problem obviously gets way more complicated at their level, because then they get into this first mile, last mile issues as well. But I think it is helpful for us to understand the transportation problem, because it's a very, very interesting sort of linear optimization problem. And having some knowledge of linear optimization is good for us, even though we never write the program to solve, the problem that Amazon is trying to solve. I think having some knowledge is useful, because maybe that can help you make some decisions around where the trucks ought to be allowed, and how do you designate truck routes and things like that. So I think just some information around congestion, the transportation problem is good. And we're going to sort of scratch the surface of the transportation problem in this class, okay? So let me go ahead and share my screen. And by the way, this is going to be the subject of the next lab as well, okay? So this is going to be the subject of your next lab. So let's first think about what is the optimization modeling. Many transportation system decisions involve trying to find the best solution, if you can somehow define what best means, okay? So the mathematics of optimization there can be a very useful tool. So there are three elements to this, okay? And I sort of remember them with like acronym DOC: decision variables, objective function, and constraint set. Okay, so DOC. So you have to remember the DOC. Decision variables are something that you control as an analyst, things that you can move around. Objective function is the quantity that you want to maximize or minimize. And constraint set are the rules that place limitations on the values of X. Okay? So maybe there is some X that cannot be higher than something, and things like that. So these are, has any of you solved this type of a problem before? Okay, I'm going to pause recording and I'm going to ask you. So there is sort of classical optimization, which is unconstrained. There could be constrained. So unconstrained optimization is something that you've done many times, where you take the first derivative, set that equal to 0, take the second derivative. If it's positive, it becomes the minima. If it's negative, then it becomes the maxima of that function. So that's sort of your constraint optimization. So there is that calculus solution. You can do that with constraint optimization as well. And that's where we get into Lagrange multipliers. You might have learned that a little bit in your calculus class. Don't worry, I'm not going to resurrect all of that discussion here. But there is like mathematical programming that you could use: the linear programming, the integer linear programming, nonlinear goal programming, dynamic programming. I think what we're going to focus on is the first one, the linear programming option. Okay, so we're going to work on the linear programming option here. So this is sort of the classical optimization. If you have a differentiable function, you want to do z as a function of f of x1, x2, x3, xn. So these x's are my decision variables. An extremum, which is the maxima or minima of value of z, exists in the solution point. of the decision variables with these asterisk represent one particular value that maximizes or minimizes the z value. Okay, so for all variables xi, dz over dxi has to be equal to 0. And this is the second derivative, what has to happen for a maxima, what has to happen for a minima. However, there could be a saddle point where the derivative is 0 as well. So if you want to identify saddle point, then this is the definition of the saddle point. I mean, if you so this is sort of the global maxima, local maximum, global maximum, and then you have the global minima. And this is sort of the saddle point looks like, which is neither a maxima nor a minima, but might still have sort of that 0 derivative. Optimization regions. These are your feasible regions, the combinations of values of decision variables for which the objective function is defined and all the constraints are satisfied. The convex region is shape of the region such that a straight line connecting any 2 points on the region boundary never crosses the boundary of the region. So this is very important when you talk about the linear optimization problem that we are going to focus on in this class. Having a convex region is very, very important. If there is no convex region, you're not going to have the solution. Okay. And I'm going to give you an example of that. So this is the example. So if you pick any point here, for example, so if I'm going to go ahead and annotate that. So let's say if I pick this point right here, I'm going to do another color here. So let's say if I pick 1 point here and 1 point here, and I do the same thing here. So if I pick 2 points on 2 edges, and if I try to connect those points using a straight line like that, I try to connect these points using a straight line. If I don't intersect with the boundary of the system or the region, then I have a convex region. But if I do intersect like I do here, it's a non-convex region. Okay, so that's the difference. If you try to join the 2 points on any of the 2 edges and you don't intersect the boundary, then it's a convex region. But if you do intersect the boundary, it's a non-convex region. Okay, and I think having a convex region is important for you to find that maximum minimum value. Okay, so go ahead and clear all the annotations. Okay, so constrained optimization. Solution is not on the boundary of a feasible region. So if it's not on the boundary, if it's an example, something like this, if it's something like this, oops. So if it's a shape like this, so you can easily find the maxima. Solution rise. So there could be a solution where solution could be somewhere in the middle, like it is here. Case 2 could be the solution is on the boundary of the feasible region. Okay. And then the boundary of the feasible region, so one example of that is if you have x1 squared times x2, such that x1 squared plus x2 squared is less than a. So then the maxima of this function would always be on that boundary of the region. Okay, it's not going to be on the edges. It's going to be always where x1 square and x2 square become less than a. So it's sort of in the circle. It's on the boundary of the circle. These are interesting problems for which a variety of solution techniques have been developed. One such technique is the Lagrange multiplier. And again, we're not going to do a lot of problems on Lagrange multiplier or anything like that. But I think it's important to just sort of refresh that from our math classes, just to kind of get our brains exercised a little bit. The classical optimization technique, which can be used when optimal solution has to exist. Constraints are equalities. So thus the solution is on the boundary of the feasible region. So if your constraints are equalities, then the solution would be on the boundary of the feasible region. And then the objective function and constraint functions are differentiable, means you can, they're continuous and you can differentiate them. Okay. And again, you know, if there's a lot of sort of variables in there, then the partial derivatives could get pretty messy for you to use. So here is a simple example. Find the maximum, minimum of this function, given some constraints. So what we do is we define a new function. We define a new function called the Lagrangian. Okay. And the Lagrangian function is basically you take your objective function, which is right here, and you subtract from that a lambda I times, and again, remember this equality. So when you use the Lagrange multipliers, these constraints have to be an equality. Okay. So remember what I'm doing here is that I'm writing this down as gi xi xn. So basically, this is the left-hand side of this equation. So this is what's being written here. And you're subtracting bi from it. So you're basically taking everything to the left-hand side of the constraint equations. And then you're multiplying that by lambda I. Okay, you're multiplying that by the lambda I, which is what we call the Lagrange multiplier. And now I'm going to m different Lagrange multipliers. Okay, but remember what I'm seeing here. I'm doing it from I to m, I equal to 1 to m, and where m is the number of the constraints I have. Okay, so whatever number of constraints I have, I'll have to do that summation for all of those constraints. Okay, so see, this is the constraint. So if I put 1 in there, the first function gives me the first constraint, second function gives me the second constraint, the third function gives me the third constraint, and so on and so forth. And the idea is then simple. You just take the partial derivative with respect to each x variable. So remember, n is the number of decision variables. Okay, so I'm going to write that down. N equal to number of decision variables, and m equal to number of constraints. Okay, and then as if lambda 1 and lambda 2 and up to lambda m, they're all sort of one variables of that equation. And then you take the partial derivative of this Lagrangian function, set that equal to 0. And setting these j functions equal to 0 will give you j equations. Setting these I equations equal to 0 will give you m equations, right? Because there are m constraints and n decision variables. And then once you have n plus m equations, you have same number of unknowns in the mix as well. So your unknowns are basically x1 through xn and lambda 1 through lambda m, right? So those are your unknowns, and you need that many equations, and you can derive that many equations by setting up the partial derivative equal to 0 with respect to each decision variables here, and then setting up with respect to each Lagrangian multiplier over here, and you'll get the m equation, and n plus m equations and n plus m unknowns. Okay. Oops. Okay. And then lambda I, this lambda I is what we call, this lambda I right here is what we call the shadow price of the constraint. Shadow price is just basically measuring, if you were to relax that constraint by 1 unit, how much you can change your objective function. If you're minimizing it, how can you can further reduce that constraint? I mean, reduce your objective function. If you're maximizing, how much you can increase your objective function if you were to relax that particular constraint by 1 unit, right? So that is lambda is the change in the objective function z if the constraint value is relaxed by 1 unit. So if you change from bi to bi plus 1, how much additional leverage do you get on your objective function? And that's why we call it the shadow price. And remember, we are in fact going to talk about this shadow price in our lab problem, even though we're not going to do any of this fancy derivatives and stuff like that. But the idea of shadow price is pretty consistent. The definition of shadow price is if you relax any one of the constraint by 1 unit, how much extra you can get out of your objective function. Okay. So let's kind of do like real quick about this mathematical problem. So let's say you have one objective function, two variables, x1 squared times x2, such that x1 squared plus x2 squared is equal to a. Okay, it's less than or equal to a. Now, you know, the good thing is that even if your constraint is not an inequality rather. So you can see here that my constraint is in fact an inequality, right? You see that? You see that my constraint here is an inequality? If my constraint is an inequality, I need to convert that into an equality. And we do that using a slack variable called y squared. And we use squared. Can you guess why we use squared in our slack variable? Why not just say x1 squared plus x2 squared plus y equal to a? If I want to convert this inequality, into an equality, why am I adding a y squared rather than just y? I did get one correct response, and that is it has to do with the sign of the inequality. Why did I use y squared instead of just using a y? Is that I know for a fact that for any real number, y squared would be a positive quantity, right? And if I want to not change my constraint, I must add a positive value to the left-hand side so that it becomes equal to a. If I just simply added y, but what if y was negative? And a real number could be negative too, right? What if y was negative? Then my constraint would not be the correct constraint that was given to me in the original problem. But having a positive value, y squared ensures that I have a positive value added into the left-hand side. And then when I'm equating it, I know y squared is positive. And that's why I'm adding y squared instead of y. If that makes sense, if that does not make sense, please let me know. I'll be happy to clarify it further. Okay, so we're calling this y as our slack variable. Then we form our Lagrangian, and Lagrangian is basically nothing but objective function subtracted by lambda, and then x1 squared plus x2 squared plus y squared minus a. So basically you rewrite the constraint as 0 on the right-hand side, and then you multiply that by lambda 1, and then you start taking partial derivative. And how many partial derivatives are going to be there? Okay, that's the next question. How many partial derivatives are going to be there? So to figure out how many partial derivatives you're going to have to take, you have to think about how many constraints you have and how many decision variables you have. And because in the couple of slides ago, we saw that the number of partial derivatives that you take to create that many equations, you take the sum of the number of decision variables and the number of constraints. So the number of decision variables in this examples are 2, x1 and x2. And then how many constraints do I have? How many constraints do I have? Okay, I see in the chat, I have one constraint. That's exactly right. There's only one constraint given here. And I have that right here that I'm highlighting right at this second. So that means I have to take 2 plus 1, 3 total partial derivatives, one with respect to x1, one with respect to x2, and then one with respect to lambda 1. Okay, so 3 different partial, and then one with respect to y. So y, you don't even have to worry about, the y constraint, because if y is equal to 0, then your constraint becomes binding, because otherwise y last constraint required either y to be 0 or lambda 1 to be 0. So that last constraint is not really helpful. The 3 of them are what you're really concerned about, the top 3 constraints, because you have 2. Remember the third one, the y only had to come into play because I don't have that, because I didn't have that as an equality. I had an inequality, and I had to introduce that slack variable because of that. But because that's not a problem for me, I mean, if I do want that non-zero shadow price, I'll just go ahead with the 3 different decision variables. And let's see. So if you were to solve these things, setting the partial derivative equal to 0, you can solve for 3 equations and 3 unknown and be able to find what those decision variables look like. Obviously, you'll have to know the value for A and all of that. Again, we're not going to do this type of a problem in our course. We're going to do mostly the linear programming problem that we can solve using Excel, and we can use solver in Excel for that purpose, because that's the alternative that we are interested in. So a popular alternative to classical optimization for problems that cannot be solved using calculus, there is linear programming, there is integer programming, general nonlinear programming, goal programming, and dynamic programming. In linear programming, objective functions are linear functions in X's. Constraints are also linear functions that are less than or equal to constants. X's are also greater than or equal to 0. Constraints define a convex region, an n-dimensional space which any 2 points are connected by a straight line lying within the space. And solution method is by heuristic algorithm, starting with a feasible solution and incrementally moving to another feasible solution. So there is a lot of jargon here, as you can see. But in linear programming, here are a couple of things that are very important to us. The objective function has to be a linear function. So the example that we saw could not be solved using the linear programming. Constraints also have to be linear functions, less than or equal to constants. X's have to be greater than 0. Okay. And then the constraint define a convex region. I gave you the definition of the convex region, where if you connect any 2 points with a straight line, they lie within the space and you never actually go outside of that space. And then the solution method is by a heuristic algorithm, starting with a feasible solution and incrementally moving to another nearby feasible solution, which improves the objective function the most. Okay. So let's try to see how we can implement it. What are some of the examples of this? Okay. So that's the example I want to work out. So you have 2 different technologies, technology 1 and technology 2. Technology 1 can maintain 3 miles of road per day, and technology 2 can maintain 2 miles of road per day. And you're deciding how much cruise should you assign. Okay, how much cruise should you assign using technology number 1? And let's say that number is x1. And what amount of cruise should you assign using technology 2, which is x2? And remember, technology 1 can maintain 3 miles per day. Technology 2 can maintain 2 miles per day. Can you write the objective function based on this information? You want to maximize the amount of road that is maintained in terms of miles per day. X1 can maintain, or technology 1 can maintain 3 miles per day, and technology 2 can maintain 2 miles per day. And so, for example, if you were to assign X1 cruise to technology number 1, you will be able to maintain 3 times X1 the road. Okay, and if you find X2 cruise to technology number 2, you will be able to maintain 2 times X2 miles of road. Okay, so if you assign one set of crew to technology 2, they will be able to maintain 2 miles of road for you in every day. But you want to maximize how much road you maintain every day. So can you think of what the objective function might look like? I'm going to go ahead and pause the video and see if you can take a guess at that. Let me try to give you a hint. So if you assign X1 cruise to technology 1, you'll be able to maintain 3 X1 as your roadway amount, 3 times x1. So I'm going to put a multiplication sign. And if you were to take technology 2 and assign x2 crew to that, you'll be able to maximize 2 times x2 amount of road, 2 times x2 miles of road. Can you now guess what is going to be your objective function? You want to maximize the total amount of road that you're able to maintain. If you assign x1 crew to technology 1, you'll be able to maintain 3 times x1 road. If you assign x2 crew to technology 2, you'll be able to maintain 2 times x2 because, you know, technology 1 maintains 3 miles per day. So I see some responses in chat. Yeah, you add them up, right? So if you add the two numbers up, that's going to be your objective function. That's exactly right. So your objective function that you want to maximize is 3 times x1 plus 2 times x2. Make sense? Yeah. I hope so. So let's say now, obviously, you can keep assigning maximum amount of x1 and maximum amount of x2 if you had unlimited resources, right? But here is some constraints where the constraints come into play. So when I say technology number 1, this is all that goes along with technology number 1. So you have to sort of have 1 supervisor, 6 laborers, 2 pickup trucks, 1 grading machine, and 2 rollers, and miscellaneous hand tools, okay? That's all goes into technology number 1. And when all of these resources come together, they maintain 3 miles of road per day. Now, for technology 2, you have 1 supervisor, 15 laborers, 3 pickup trucks, no grading machine, no rollers, miscellaneous hand tools. And when all these resources come together, they maintain 2 miles of roadway per day. Okay. Now, here the constraints come in. You can only have 150 laborers. You can only have 40 pickup trucks. You only have 30 rollers. You only have 10 graders, and you have to have 6 supervisors. You have to have. So this is a different type of constraint now. It's not that you need minimum. You can only have 6 supervisors. It's maybe the government agency that is asking you to maintain the road. It's telling you that, hey, you can't just have laborers just working on their own. You have to have some engineer, supervisor, or whatever. And you have to have at least 6 supervisors in the mix. And hand tools are unlimited. So hand tools, nobody cares. You can use whatever. Okay. So now, I told you already what your objective functions are. Let's try to write down these constraints, okay? Let's think about, remember, you're trying to figure out how many x1, how many x2. So let's look at technology 1 first. They both use just 1 supervisor. Okay. So now assume that you're applying the amount of technology or amount of these sort of combinations that you're applying is x1, right? So if you're using x1 amount of technology 1, how many supervisors are you going to be using? That's the question. How many supervisors are you going to be using? So let's try to annotate that. On this slide. How many supervisors are you going to be using if you're not just using 1 unit of technology 1, but you're using x1 units of technology 1? How many supervisors you're going to end up using? Pause. So yeah, I see it. So if 1 unit of technology 1 uses 1 supervisor, that means if I'm using X1 units of right? So if I'm using X1 units of technology 1, I'll be using X1 number of supervisors used will be X1. Now let's think about if I'm using 6 laborers for 1 unit of technology 1, but I'm employing 6 units or sorry, X1 units of technology 1, how many laborers am I going to be using? You should be able to figure this out. I'll wait. Okay, that's right. Because each unit of technology 1 uses 6 laborers. If I'm using X1 technology, X1 units of technology 1, I'll be using 6 times X1 as my number of laborers total. And same idea here. If I'm using 2 pickup trucks for each unit of technology 1 grading machine, so then that kind of gets me back to X1, and 2 rollers, it gets me to 2 right? Make sense? Now I can do the same thing for technology number 2, same exact idea, but this time I'm going to be doing it based on technology number 2. So I'm going to just write it down over here. For X2 now. Supervisor will be just simply X2. $15 laborers, so it's going to be, so laborers used will be 15 times X1. Makes sense? Sorry, X2 rather, because remember, the technology 2 we're talking now. 3 pickup trucks, 3 times X2. No grading machine, so that wouldn't matter. No rollers, compactors, that doesn't matter, and miscellaneous home to home don't matter either. So there is no constraint related to grading machine or rollers or compactors because technology 2 doesn't use any. It's a very, you can think of this as a more labor intensive sort of technology. Is this clear to everybody? Let me put this out over here because then I can start writing my constraint equations. Questions about this? No questions here. That's good. So now let's write the equations of the maximum of 150 laborers. How would you write constraint based on that? So I want to write the constraint based on 150 laborers. So what that constraint looks like then. Which one was the laborer one? I know these are not in the correct order. So maybe I should correct this. So maybe I should write down these constraints. So this was based on supervisor, if you recall correctly. And then this second one was based on laborers. Third one was based on pickup trucks. Fourth one was based on, I'm going to say rollers. And fifth one was based on graders. Okay, so these are the different constraints. So now let's take each of these constraints. So let's talk about the supervisor constraints. It says minimum of 6 supervisors must be used. How do you write that as a constraint? If you have to use minimum of 6 supervisors, so I'm going by this one, minimum of 6 supervisors must be used. What does that constraint look like in the equation for? I'm going to go ahead and pause, and I'm looking for some answers. Yes. So if I'm using X1 units of technology 1 and X2 units of technology 2, and I'm employing I need to employ at least 6 supervisors. So my total number of supervisors employed will be x1 plus x2. And I want those to be greater than or equal to 6. Okay. Similarly, now I can write the laborers constraint. What's the total number of laborers am I going to be using if I'm employing x1 units of technology 1 and x2 units of technology 2? Okay, I see some responses already. That's pretty quick. That's good. Yes. Oh, no, I think the laborers one is, the laborer is 150. Okay. So this would be 6x1 plus 15x2. Sorry, the order is a little bit messed up here. Should be less than or equal to, because you can only employ 150 laborers. So that's my labor equation. So pay attention to this order is a little bit messed up, but pay attention to the write up here. And then pickup trucks is 40. And for pickup trucks, I have the equation 2x1 plus 3x2. So this 2x1 plus 3x2 should be less than or equal to oops. Less than or equal to what? Let's see. Pickup trucks is 40, so that will be the 40 number. Okay. For rollers, max of 30 rollers, that means x1 has to be less than or equal to 30. And for grader, I have to check that number if I'm doing it correctly. 2x1 should be less than or equal to 10. That makes sense. I want to go back real quick. To the, let me go ahead and pause.